Hello and welcome to the Chemistry Academy. In this video we're going to be looking at the Advanced Higher Level VSEPR theory subtopic, also sometimes pronounced VSEPR, you can see it as VSEPR. This theory is important for you to know when asked in your SQA Advanced Higher Chemistry exam about the shape of a molecule or a polyatomic ion. Polyatomic ion is something like NH4 positive, where you've got a lot of atoms in, or more than one atom in the ion. So the way that VSEPR theory works is that it's based on the fact that electron pairs will repel each other because they are all negatively charged. So we know from doing quantum numbers that electrons can pair as long as they have opposite spins, but then once you then get multiple electron pairs, they would then repel each other. Because of this, if you have pairs of electrons around a central atom in a molecule, those pairs of electrons will then space themselves out and arrange themselves around the central atom so that they're minimising the repulsion that they experience from each other as much as possible. So it's all about trying to get your pairs of electrons as far away from each other as you can. Okay. Now there is an equation type thing sometimes people do for VSEPR theory. It's more like a sum. However, personally that's not how I teach it because I feel like it stops you from understanding how it then relates to the fundamental shape of the molecule that you kind of learned at National 5. So this is the way that I work out the shapes of molecules using VSEPR theory principles. It's maybe not the way that you got taught it in school, but if you're struggling with it, maybe keep watching and see if it ends up being something that resonates better with you. So I've got some examples here. We're going to do probably about 10 examples altogether of how we use VSEPR theory to work out the shapes of molecules. So all of these are molecules. We don't have any polyatomic ions in it yet. They'll be on my next 5 examples. And I will put a little table on the video. It's different stages. That is a good table for you to copy down into your summary notes and to help you learn what the different shapes are and what they kind of look like. So when I'm looking at the shape of a molecule, I start off by using, like I said before, my National 5 knowledge. So a lot of these molecules we would have drawn at National 5 very straightforwardly, just thinking about their basic shape. So water we know is H2O. So we would always draw it like this. We know that's its shape. This is because the valency of hydrogen is 1 and the valency of oxygen is 2. So we know that the hydrogen will make one bond to the oxygen and the oxygen will make a bond to each of the hydrogens. When it comes to VSEPR theory though, we don't just look at the bonds, we need to look at all of the valence electrons around the central atom. So we know from National 5 again that one covalent bond contains 2 electrons, one shared pair of electrons. So we can draw those in there. That's a shared pair of electrons. So at the moment, the oxygen has given 2 electrons away, okay, 1 to each of the covalent bonds. But oxygen has 6 valence electrons because it's in group 6. If you look it up in the periodic table, on the electron arrangement page, you'll see its outer electron arrangement is number 6. So we've drawn in 2, which means there's 4 valence electrons left. So we need to draw them in. Those 4 valence electrons will pair off, giving me 2 what we call lone pairs. So these electrons here would be classed as a bonding pair because they're involved in a covalent bond. These 2 here are classed as lone pairs because they are not involved in any bonding at this point in time. So because we then have 4 pairs of electrons around the atom, like I said before, they are all going to space out as evenly as possible in order to minimise the repulsion. These lone pairs repel these electrons in the bonds, and that's what pushes it down into an angular, or sometimes called bent, structure. So the shape of this molecule is angular because you've got 2 bonds, but then the 2 lone pairs are repelling things down. Okay, and again the picture that I'll put up should show you that in the diagram as well. For carbon dioxide, we know that carbon dioxide is, so carbon's got a valency of 4, oxygen has a valency of 2, So it looks like this. Each bond has a pair of electrons in it. So that's 1, 2, 3, 4 bonding pairs of electrons there. That means that carbon has given 1, 2, 3, 4 electrons away because it's made 4 bonds. It only has 4 valence electrons because it's in group 4, which means there are no more electrons around this central carbon atom. It had 4 to start with because it's in group 4. It's given away 4 to make those 4 bonds, so there are no lone pairs around this central carbon, which means this is the finished structure, if you like. There's no electron pairs up here to cause any repulsion. So this is linear because it's in a straight line. Okay. For NH3, again, we've drawn this plenty of times at National 5. Okay, we know that it's got this sort of trigonal pyramidal structure that it's called. The reason it's got this trigonal pyramidal structure and not this, where this would be the bonding pairs as far away from each other as possible. Nitrogen, which is a central atom, and that's what we're always concerned about when it comes to VSEPR theory, it's in group 5, which means it has 5 valence electrons. It's currently given away 3 to form those bonds, so that means it has 1 lone pair left, 2 left, which makes a lone pair. That lone pair then repels these bonding electron pairs, so that's what forces it into this trigonal pyramidal structure. The repulsion from the lone pair repels the bonding electron pairs and causes this trigonal pyramidal structure. Okay. So then BF3, we've got a boron. This is like a newer molecule we probably didn't really draw at National 5. We've got boron, and then there's 3 fluorines, so we'll just at the moment draw them equidistant just in case there's no lone pairs. That means we've got bonding pairs, 3 of them, because there's 3 fluorines attached. If we look at boron on the periodic table, it's in group 3, which means it only has 3 valence electrons. That they've already been drawn in, 1, 2, 3, which means there's no lone pairs. So this is how the molecule stays. The bonding electron pairs are as far away from each other as they possibly can be. This is a 360-degree circle. 360 divided by 3 is 120. So each of those bond angles is 120 degrees. Okay, that gives the even spacing around the 360 degrees. So this shape here is known as trigonal planar because it's got the 3 points, the trig bit, and the planar just means it's like flat, like a pancake. So if you imagine this just flat to the page, there's nothing pointing backwards or pointing forwards. Whereas in the trigonal pyramidal, this hydrogen would be pointing forwards, and like maybe this one would be pointing backwards, and this one would be flat to the page. So the wedged bonds mean it's pointing forward. If you were to put your face to the whiteboard, it would poke you in the eye. The hashed bonds mean it's pointing backwards, so if someone was on the other side of the whiteboard and put their face to it, it would poke them in the eye. And then the solid bonds are just with the straight line, are flat to the page, so they would poke anyone in the eye. I think I'm going to have to change my pen because that one's running out. If we then go on to PF5, so we've got a central phosphorus, and then we're just going to loosely draw 5 fluorines around it. Okay. So there we've got 5 bonding pairs because 5 covalent bonds have been made. If we look up phosphorus, we'll find that that's in group 5, which means it has 5 valence electrons. We've drawn in 1, 2, 3, 4, 5, 1 is given to each bond, so there's no lone pairs here. So that means that these bonding pairs will all space themselves out equidistantly, and this structure in 3D space is known as trigonal bipyramidal. So it kind of forms the triangle shape in the 3, and then these atoms are in a straight line. This one doesn't come up very often, but it is worth knowing about it. But on the diagram I'll put here, it'll show the wedged and hashed bonds for you to make it a bit clearer as to what that shape looks like. So we'll go and do some polyatomic ion examples now, and then hopefully that will give you a good idea of how to draw your VSEPR theory molecule shapes. Okay, so let's do some polyatomic ion examples, although this one is another molecule just because we have one more shape to show you. So SCl6, we've got a central sulfur with 6 chlorines around it. So again, we'll just drop that down. We then know we've got 6 bonding pairs of electrons because there's 6 bonds around the central atom. And then if we look up sulfur on the periodic table, we should find that that's in group 6, so that's got 6 valence electrons, which means there are no lone pairs here. This shape then, therefore, is called octahedral. So I know we're usually used to octahedral being where you've got 8 being oct as an octopus, but in this context, it's actually for the prefix for 6. I'm not actually 100% sure why that is. I don't know if it's just because of the different language of prefixes. But octahedral, just remember, for the shape of a molecule is 6 atoms around, or 6 bonding pairs around the central atom. In terms of the wedge and hash bonds, these bonds in the middle tend to make a point out, and then the ones here point back, so they kind of make like a square, a planar square, and then this chlorine points up and this chlorine points down. Okay, for this one here, we've got an oxygen and 3 hydrogens, so that's 3 bonding pairs. Oxygen is in group 6, which means it has 6 outer electrons. This positive charge here though means that there's 1 electron being lost. So 1 electron's being lost, which means that although it had 6, it's lost 1, which means it would only have 5 valence electrons. So we've drawn in 1, 2, 3, which means it's just got 1 pair left. Okay, so this gives us like a tetrahedral, or not tetrahedral, but it looks like a tetrahedral arrangement because it's got 4 electron pairs, but because this one is a lone pair, it's still classed as trigonal pyramidal. And in terms of the wedged and hashed bonds, one of the bonds is straight, one of the bonds is wedged, and one of them will be hashed. And that creates the equal distance of all the hydrogen atoms and the bonding pairs to minimise the repulsion. This one here, NH4 positive, we've got the central nitrogen and then 4 hydrogens. So we've got 4 bonding pairs. There's a positive charge again, which means that the nitrogen's lost 1 of its valence electrons. So it usually would have 5 because it's in group 5, which means it now only has 4, and we've drawn in those 4 in the bonding pairs. So this actually ends up as a tetrahedral structure. So hopefully you remember this from National 5. It's like a 4-headed monster. So this polyatomic ion NH4, which is ammonium, is tetrahedral. In terms of the wedged and hashed bonds, again, one's straight, one's wedged, one's hashed, and then that one is straight as well. The bond angle in tetrahedral is a bit of a weird one, is 109 degrees, and that's just one that you need to remember. Okay, so the bond angles in tetrahedral structure are 109 degrees, and that's the angle that gives the minimal repulsion between the electron pairs. If we then move on to this xenon oxide, sometimes you will get compounds that have noble gases in it, but after us telling you for years that noble gases don't form any bonds. Anyway, let's just ignore that fact. So we've got the central xenon, and then we know oxygen has to make 2 bonds, so they're going to be double bonds. So this is where, again, where your National 5 knowledge plays a big part in it, because you need to know how many bonds each atom needs to make to satisfy its valency. Xenon is in group 8, which means it has 8 valence electrons. there will be it's made 1, 2, 3, 4, 5, 6. So that means there's 6 bonding pairs. 6 of those have come from the xenon. 6 of those electrons have come from the xenon, so that means it's got 2 left, so it would have a lone pair. Now that lone pair is going to repel things, so if I redraw this, it's going to end up with, if the lone pair is up here repelling, it is going to end up with a trigonal pyramidal type structure. In order to minimize the repulsion. Okay. Then we've got PF6 minus. So we've got the central phosphorus, 6 fluorines. And we usually know anything with 6 things is octahedral. Yeah, that's usually a bit of an easy one to remember. You don't need to draw the wedge and the hash bonds in your exam, but if you do draw them, they do need to be correct. So our phosphorus, there we've got 6 bonds, so 6 bonding pairs of electrons. Phosphorus is in group 5, so normally it would only have 5 valence electrons, but this negative charge tells you there's 1 extra electron on it. So that means it would give it 6 valence electrons, which has allowed it to form all those 6 bonds, and therefore there's no lone pairs. That would be octahedral. I should have also said when a polyatomic iron's got an overall charge, normally rather than writing the charge in the middle, we would put square brackets around it and put the charge on the outside. So I probably should have done that for this one as well. Okay, so square brackets and the charge on the outside. Same for this one. Okay, and then I've got one last example down here, the positive nitrogen dioxide. So again, using our National 5 knowledge, we know that nitrogen forms 3 bonds, oxygen normally forms 2, so these are going to be double bonds because the oxygen needs to form the 2 bonds. The nitrogen would normally have 5 valence electrons, which it's made 1, 2, 3, 4 bonds, which means it's given 4 electrons away. But the positive charge, remember, means that 1 electron has been lost, so it technically only has 4 valence electrons. So that would be the final shape. There are no lone pairs, so that would be linear because it's in a straight line. And again, the positive charge goes on the outside of the square brackets. Should put up here, this means that 1 electron gained. Okay, so just remember, if the polyatomic ion's got overall positive charge, it means that the central atom lost a valence electron in the process. If it's got the negative overall charge, it means it's gained a negative electron in the process forming the substance. Okay, so I hope that helps you out with VSEPR theory. These are probably most of the molecules that you will come across in your SQA Advanced Higher chemistry exam, but it's just a good idea to have a sheet like the table I've posted in the video a few times. Have it stuck up on your wall where you revise, so you look at it regularly, just so you get used to seeing the shapes of the molecules and what they look like and how the shape, like what each shape is named. Okay, and then other than that, it's really just using your National 5 knowledge of valencies and electron arrangements to then work out if you've got any lone pairs or not. One last thing actually I was going to touch on just to finish, while I remember, is sometimes you'll get asked about just lone pairs around the outside atoms as well, not just the central ones. So again, it's the same knowledge. For this chlorine, it's made 1 bond, so that's used up 1 valence of its valence electrons. It's in group 7, so it would normally have 7. So if it's used 1, that means it's got 6 left. So it's got 3 lone pairs around it. Okay, this is known as a Lewis structure where the electron pairs are shown. So if you get an exam question on that as well about lone pairs on other atoms, not just the central one, it's the same theory. You just see how many bonds it's made, what is its valence, how many valence electrons does it normally have, and therefore take those numbers away from each other and then work out how many lone pairs it must have. Hydrogen never has any lone pairs because it only has one electron to form the one bond. Fluorine is also in group 7, so if it's made one bond, it's going to also have 6 valence electrons left, so it would also have 3 lone pairs, and every single one of those fluorines would also have the same. The oxygen here, just to finish off, it's made 2 bonds, it's got 6 valence electrons, so that means it's got 4 electrons left, so that would be 2 lone pairs that they've got. Okay, so in terms of being asked which molecule has the most overall lone pairs, it would be either this one or this one, because they're going to have 3, 6, 12, blah blah, whatever 3 times 6 is. That's really bad, I don't know that. 18 lone pairs, whereas this one's got 2, 4, 6, 7. Okay, so hope that helped. If it did, please give this video a like. Don't forget to subscribe. Tell all your chemistry friends about my YouTube channel, please. And if you are studying Advanced Higher and you would like to do more practice questions, more quizzes, and get feedback on your answers, you might want to consider joining my Advanced Higher Chemistry Revision Google Classroom. You can find more information about that on my TikTok page at the Chem Academy. So thanks guys, and I'll see you again soon.